I would like to thank the organizers for inviting me to give this talk. This talk will be somewhat different from the previous ones regarding its topic. I will talk about a very specific graph optimization problem, namely multi-way cut, that hopefully you are all familiar with. And in the first half of the talk, so this is an earlier work that we did with Kartik, Tamás, and Vivek. And in the second half of the talk, or at the very end, if I still have some time, then I will talk about some possible extensions, recent extensions that we did with Tamás and a student from Budapest. Okay, so let me define the problem setting first. So in the multi-way cut problem or k-way cut problem, we are given an undirected graph with a non-negative weight function. And the goal is to delete edges of this graph such that you separate. And we are also given k terminal vertices. And the goal is to delete a minimum weight subset of edges such that you separate all the terminals from each other. It's a very basic problem. One of the toy examples on courses on approximation algorithms, because you can find, as you will see, a very simple two approximation for this problem. So what do we know about this problem? So in this example, you can, for example, delete this you can consider this cut shown by this red part, which means that you delete these edges and then you separate it, all the terminal vertices from each other. Okay, so what do we know about this problem? If you only have two terminals, then the problem is very simple. It's just simply the ST cut problem, right? And we can solve it in polynomial time. However, it turns out that already for three terminals, the problem becomes very difficult. It's NP hard. We cannot solve it up to optimality. And it's just a naming convention. So when k is part of the input, then I will call the problem as multi-way cut. Okay, so in multi-way cut problem, I'm not specifying the number of terminals. Okay. The nice thing about this problem is that there's a very simple two approximation, which is due to Dalhaus and co-authors. And I will even show this proof for you because it's good to see that you can get such a result a simple way. So the idea is the following. Let's consider the terminal vertices, and for each terminal, let's take a cut, a minimum weight cut, which separates the given terminal from all the remaining terminals. This can be solved because this is, again, just an ST cut problem, right? So for every terminal, we can find a cut which separates it from the rest of the terminals. And that what you can do is the following. We order these cuts that we obtained in an increasing order according to their weight. And we take the union of the k-1 smallest one. So we throw out the last one because it's not needed. Why is this good? Because, I mean, if you take the union of these cuts, then that means that because Zi is included in this union, where Zi is the cut separating the ith terminal from the remaining ones, this will separate everyone from everyone else. You do not need the last cut because all the other cuts were separated already. Okay. And this gives a two approximation because if you consider an optimal solution for the k-way cut problem, then you can consider the set Zi star, which is the part containing the ith terminal vertex in the optimal solution. And clearly, since we take a minimum cut in this step, in the second step, the weight of the minimum cut is smaller or equal than the weight of the cut of this part in the optimal solution. And this simple calculation shows that you get a two approximation. Actually, it's even better. It's 2 minus 2 over k. Okay, this is nice. So we can get a constant approximation for the problem. How can we prove this further? The idea is to use LP relaxation. So first of all, I want to consider an IP formulation of the problem, take and apply some kind of rounding technique, which means that we take an IP formulation of the problem, we consider the LP relaxation, we solve the LP relaxation, we get some solution x star, and then we want to round this solution to get an integer solution. Okay, so usually when you apply such a technique, then and you want to analyze it somehow, then you are interested in the following values. So here in this picture, this bottom line denotes the value of the optimal fractional solution. Okay, this is something that we can compute because we can solve the LP. And here in the middle, you can find the optimal solution for the integer problem. Okay, so that's the integer optimum. We are interested in this value here, but we cannot compute it. And then while doing this rounding technique, we get some integer solution, which is, of course, cannot be better than the optimal integer solution. So what's the approximation factor of an algorithm? Is the gap between these two, right? Unfortunately, we cannot compute this because we don't know this value. That's exactly the problem. So instead of saying that, and when you analyze such an algorithm, then instead of saying that this gap here is small, maybe we can consider this gap here, denoted by B, which is the ratio between the optimal fractional solution and the value of our solution. And if we can verify that this gap here is small, then that also proves that the other gap, the one that we are interested in, is small as well. That's a very simple idea. So usually when you do a rounding method, then that's how you can analyze your algorithm. There is this third gap here between the optimal fractional solution and the optimal integer solution, and this is an important value. This is called the integrity gap of your LP. And this picture already shows that, okay, so we want to somehow bound the value of A using B, but there's no hope for proving that B is small if this integrity gap is large, right? Because the integrity gap gives a lower bound for the value of B. That does not mean that you cannot approximate the problem, but your rounding technique will not work in this case. Okay, that's the implication. However, there are certain, and it's a very interesting thing, I think, for the first sight. So it turns out that there's a surprising consequence of the unique games conjecture. I will not go into the details of unique games conjecture. If someone is interested, I still have some slides at the end of the talk, and I'm very happy to show those. But there's a conjecture which is called the unique games conjecture, and the surprising consequence of this conjecture that for certain LPs, if you can verify that the integrity gap is large, that already implies that you cannot approximate your problem well. Okay, which is somehow, it's intuitively this shouldn't be the case, because see, the gap here has nothing to do with the gap there, but still it turns out that you can verify that in certain cases, if you prove a large integrity gap for a certain LP, then that proves that you cannot approximate your problem better than a certain factor.
So do you mean that for the natural LP relaxation of the...
No, that you need to find the right LP for that. So it depends on the LP, but yeah, I will talk about this in this case. Okay, so what is the naive LP relaxation for multi-K-cut, for example? The multi-K-cut problem, the naive LP relaxation is to minimize, so I denote by, I have binary variables denoted by xe for every edge, which denotes whether I delete that edge or not. And I want to minimize the total sum of the edges, or the weight of the edges that I deleted, subject to what? For every path from going between two terminal vertices, I denote the set of such paths by Pig. I want to choose at least one edge. That's a very naive, simple formulation of the problem, and this is already the LP relaxation. Okay, so you can write up an IP, and if you consider the LP relaxation, you get this. The integer solutions are exactly the KV cuts for this problem. What can we say about the integrity gap? It turns out that the integrity gap of this LP is exactly 2 minus 2 over k, the same as the approximation factor that we obtained before. The tight example is taking a star, the terminals being the leaves of this star. So that means that if we start with this LP and we do some kind of rounding, we will not get anything better than what we had before. You need to come up with something more clever. Okay, so let's try to find a better IP formulation. And if you think about it, then what happens in the multi-K-cut problem, then basically you partition the vertex set into k parts if you have k terminals. Every terminal has its own part, and that means that for every vertex I can introduce these variables, again binary variables, denoting whether the given vertex goes to the ith part. Okay, so xiu for a given vertex u will somehow encode whether this vertex u will go to the part of the ith terminal or not. Okay, this is the idea. And once you have this, then how can we somehow characterize the edges that are cut? So for the edges as well, I can introduce variables denoting whether a given edge, y, e, I will denote whether the given edge is in the cut corresponding to the ith part. And the connection between these variables is that the value of the y variables can be expressed by using the axis. Okay, so if an edge is cut, if it goes between two vertices corresponding to different parts, that's the simple observation that we are using here. You don't have to stare at the formulation. I will write up the concrete LP relaxations. Okay, so basically, if you starting from this idea, you can write up the following LP relaxation. We have these variables corresponding to the vertices, whether a given vertex goes to the ith part or not. For the edges, we have seen that we have this connection between the edge variables and the vertex variables. And if you take the relaxation, so you forgot about the integrality constraints, then basically what you get is that because of this constraint here, so what does this constraint mean? This means that we want to put, originally that means that we wanted to put a given vertex on only to one part, but now, because we are considering the relaxation, that means that basically, if you think of these x, u, y values as coordinates, we have k such values, then that means that this can be represented as a point in k dimension, and the constraints tells us that we are in this simplex, right? So we are on the hyperplane where if we sum up the coordinates, then the sum is 1. Okay, so this leads to the so-called CKR relaxation of the problem due to Kalinescu, Karlov, and Rabani, which says that the multi-way cut problem, the k-way cut problem, can be somehow relaxed. So we can write up the IP, and the IP relaxation will be the following. We want to basically embed the vertices of the graph into this simplex, which is denoted by delta k. So that's once again, the set of elements, non-negative, set of vectors whose coordinates sum up to 1, with non-negative coordinates, such that, of course, we fix the positions of the terminal vertices. The terminal vertices will go to the vertices of the simplex. Okay, and the CKR relaxation, this is the starting point of our investigations. It turned out that this is a very nice relaxation. It has a lot of implications. Here is just an example showing that if you start with this graph, then the CKR relaxation gives you something like this. Not that interesting. Okay, so what do we know about the approximability and inapproximability of multi-way cut? So we had this 2 minus 2 over k approximation, which was a very simple commutative algorithm. And then using the CKR relaxation, Kalinescu, Karlov, and Rabani improved this approximation factor to 3 over 2. And then later, independent work improved the approximation factor for the 3-way cut problem. And the 3-way cut problem, I'm mentioning it here because it will be crucial in our algorithm as well, or in our proof as well. So it turned out that the 3-way cut, you can improve the approximation factor to 12 over 11. And then, I mean, there's a long line of results here, but the currently known best approximation factor is slightly below 1 over 3, 1.3. Okay, so this is what we know about approximability of the problem. So what do we know about inapproximability? It was already shown in an earlier work by Freund and Karlov that the integrality gap of this, the CKR relaxation is at least 8 over 7, which is, okay, that only means that if you start with this relaxation, then we cannot hope for a better algorithm than this. But the interesting thing is this result here, because Manokaran and the co-authors showed that the approximability of multi-way cut, assuming the UGC conjecture now, so this is one of the examples, but when we have this thing, the integrality gap, so the approximability of multi-way cut is at least, sorry, not exactly, but at least the integrality gap of the CKR relaxation, which is a very, very strong result. So that means that if you want to somehow improve the the lower bound for the approximability of this problem, then it's enough to improve the integrated gap of the CK relaxation. So you need to verify that the integrated gap is large enough. And there's a recent, the best inapproximability result before our work was this roughly 1.2. Okay, so that means that at this point we have an approximation factor of 1.3, and the inapproximability is 1.2, and the question was the real value between the two. Actually, the question was whether the right answer is 1.2, because it's just a nice number. Yeah. Okay, so in order to understand the idea of the example, we will first have a look at the gap example for three-way cut. And it turns out that you can make a lot of simplifications. For example, we will work with this very special graph. So this is the triangulated simplex that we have here. So it has two parameters. Actually, I will restrict my attention to the case of the two-dimensional simplex, so with three terminal vertices, and we have another parameter n, which is just the number of denotes the number of vertices on one side of this simplex. Okay, and the edge set of this triangulated graph will be denoted by this E3m. Okay, so you can think about, as we discussed, you can think about a cut as a partitioning of the vertex set of this simplex into k parts. But actually, for some reason that will be clarified later on, it makes sense to use k plus 1. Let's call them colors, because you can think of it as a coloring. It makes sense to use k plus 1 colors instead of k. The k plus 1th color will denote the vertices that are not in any of the parts corresponding to the terminal vertices. And if we are using k plus 1 colors, then we will call a cut a non-opposite cut, which is, at this point, it's not clear why non-opposite cuts are interesting. So we call a cut a non-opposite cut. Maybe I will show the picture because it's easier to understand. If for every point of this simplex, the color of that point is either this dummy color, the k plus 1, or it's a color which appears in the support of the given point. Okay, so for example, this first cut is not a non-opposite cut because we have some points on this side of the simplex having color 1, and that's forbidden. Okay, but the other two cuts are non-opposite cuts. And why are we interested in non-opposite cuts? The reason is the following. So if I denote by tau k the integrated gap of the CK relaxation with k terminals, okay, and tau kn, the gap between x star is just the solution. This is the simplest solution that you can think of for this triangulated graph that I showed you before, which embeds this graph as you would expect it to the simplex. So every point goes with the edges having the same length. So I denote the gap between this solution and the optimal solution using only non-opposite cuts. Okay, so I restrict my attention to non-opposite cuts, which is just a subclass of cuts, possible cuts that we have. Then Angelidakis et al. Showed that actually this latter gap is very close to the first one. So observe that we are interested in the integrated gap of the CK relaxation, but instead of that, since the difference between these two is small due to this result, it's enough to lower bound this special gap, which only considers non-opposite cuts in this graph. Okay, so the essence of this result, so if you specify, for example, if you apply it for the case of 3 terminals, then this already gives you a 1.2 inapproximability result. That's how they obtain this. So the conclusion, and even without remembering what was the notion of a non-opposite cut, so the main conclusion is that it's enough to construct an instance if you want to improve somehow the inapproximability result, which means that you want to prove large integrated gap for the CK relaxation, it's enough to construct an instance, which means that you just have to find the weights on the edges of this triangulated graph, such that this instance has large integrity gap against non-opposite cuts. You don't have to consider any other cut. It's enough to concentrate on non-opposite cuts. And in the two-dimensional case, so when you have three terminal vertices, the situation is even better because they show that among non-opposite cuts, it's enough to concentrate on so-called ball cuts, which looks like this, or three-corner cuts, which looks like that. And for that reason, it's easier to work with the two-dimensional simplex. That's how they could improve the lower bound. Okay, so how can we even further improve the lower bound? And that was the question that we were interested in. So the good news is that once again, it's enough to improve the bound for some tau k and for some k, which was this gap against non-opposite cuts. The bad news is that for the case when you have three terminals, basically everything is known. So there is a lower bound, which is 1.2 roughly. The upper bound is 1.2. So that means that you have to use at least 4 terminals, which means that you are working with the three-dimensional simplex. In the three-dimensional simplex, we don't really understand the structure of non-opposite cuts. So somehow that was the main obstacle in improving the integrity gap, that we don't have a nice theorem like this corner cuts and ball cuts statement in the two-dimensional case. And the main result is that we improve the lower bound in the 4th digit from 1.2, which is not a huge gap, but the main point is that it's not 6/5. That's I still have to work on how to sell this result better. But the main point is that the gap is not 6/5, and I think the interesting thing is not the bound itself, but the technique that is used in improving the bound. And we are hoping that somehow you will see the idea can be used to further improve the lower bound. So the approach is the following. We know that it's not enough to use two-dimensional instances, because in the two-dimensional case, everything is known. So we will take a convex combination of some specific two-dimensional instances and a single three-dimensional instance. And we analyze these instances against non-opposite cuts one by one. And then we choose the coefficients in the convex combination in such a way that the three-dimensional instance that we obtain is bad against any non-opposite cut. That's the idea. We need one more definition, and it's a similar thing than non-opposite cuts. So a cut will be, maybe it's better to have a look at the picture. So a cut is called a fragmenting cut if it intersects every side of the simplex at least 2 times. And otherwise, I will call it a non-fragmenting cut. And it will be clear soon why this is interesting. Okay, so the first instance that will appear in our construction is just the same instance that appeared in the previous paper that I mentioned for the case of 3 terminals. It's a special instance, 2-dimensional instance. So this picture here is the graph that we want to construct. We are working with this simplex, and what happens here is that we copy this 2-dimensional instance to this face of the simplex. Okay. And in the previous paper, they observed that this instance has gap 1.2 against non-opposite cuts. So that was their idea. Actually, it turns out that you can somehow make a fine-grained analysis of this observation, and it turns out that this gap is strictly larger than 1.2 if the cut is non-fragmenting, and this face here has a lot of nodes with this 5th label that I mentioned, that there is this extra label. Okay, so the main takeaway from this slide is that, okay, so we have this gap living on that face of the simplex, and it has gap 1.2 in general, but in certain cases, this gap is much larger, which is great because that means that against those kinds of cuts, this is a good instance. Okay, the second instance is again a very simple 2-dimensional instance living on the same face of the simplex, basically we write uniform values on the sides of the simplex. And maybe that's the point where it becomes clear why fragmenting cuts are interesting. If you have a fragmenting cut, then that means that it will cut every side of this triangle twice, and it will have huge value. Okay, so that's why we are interested in fragmenting and non-fragmenting cuts. So by adding this, dropping this instance in the pool, we will ensure that fragmenting cuts will be huge. Okay, the third instance is the single three-dimensional instance. It's again very simple. For every edge of this huge simplex, we write a uniform value. And it follows from an earlier result by Mirzakhani and Vondrak that this has large gap against non-opposite cuts with no node of label 5. So if you are not using this fifth label that I was mentioning, that this already has large gap. But it turns out that even if you have this fifth color used in the coloring, then you can still say some kind of a similar statement. So it turns out that this instance has large gap, where the gap is parameterized by the fraction of nodes having labels 1, 2, or 3 on this face. Yeah, on this face. Okay, so there are a lot of technical details here. Basically in all instances, what we can state is that there were some previous observations, but you can giving a more detailed analysis of these instances, you can somehow state something stronger on the integrated gap stuff. Okay, so what do we have so far? So we have these three instances, and every instance is good against certain kind of cuts. Okay, so if, for example, when we had the fragmenting cut, then we observed that the second instance is bad against those. So bad means that it has large value. Every cut has large value on those instances. So this is already very promising because basically we covered everything. But it turns out that if you want to, and we are not going to the details of the computations, if you want to optimize, so you basically you write up a general convex combination of these instances, then it turns out that you can identify a ball cut with a given cost and the corner cut with a given cost. And if you optimize, then it turns out that you get exactly 1.2. So the best you can get out of this is 1.2. So that means that you have to throw in something else. And for that reason, we need a fourth instance, which is again a two-dimensional instance living on the same face of the simplex as before, and it has positive weights only in the corners of this simplex, of this two-dimensional simplex. On the edges of these, I mean, this is a constant fraction of the side of the simplex, but you need to write positive values on those edges. And it turns out that if a non-opposite cut has small weight both on instance 1 and 3, then it must contain red edges, which means that this instance will add to the cut value there. And once you do the computations, which is the ugly part of the proof, then it turns out that if you optimize these parameters, we did this by hand, then you get this lower bound. We were very happy to see that at least you can go above 1.2. You might ask whether this is the best that you can get here. We don't know, but using these four instances, actually you can show that there's not much space for improvement. So I think we can verify that just using these instances, you get an upper bound of what you can prove here, where you have 6 instead of 1 in the 4 digits. So just using these 4 instances, we are not helped too much. But the main point is that if you can come up with other instances, even in 3 dimensions, that behaves nicely against these non-opposite cuts, then you can maybe improve the bound by combining those. Okay, do I have like 1 more minute to? Okay. So let me mention just a possible extension of the multi-way cut problem, because this is something that we did recently. So one possible generalization of multi-way cut is the following. We are given again an undirected graph with edge cost, and instead of terminals, we are given terminal sets. For instead of k terminals, we are given k terminal sets. And what we want to do is that we do not want to separate these terminal sets from each other completely. But instead of that, we will choose terminals in these terminal sets, and we only want to separate those from each other. This is not a well-defined problem. I will give you a list of possible definitions. Okay, so what kind of variations do we have? So for example, one possibility is that for every terminal set, you have to choose one given terminal, and then you need to delete edges such that you separate these chosen terminals from each other. Okay, so it's like a two-step version of multi-way cut, because first you choose the terminals and then you delete the edges, and you have to optimize with respect to both of these steps. Another possibility is to choose a terminal from every terminal set, but it's a bit more complicated. So we want to, the choice can also depend not only on the terminal set itself, but from the other terminal set from which we want to separate it. Okay, so for every pair I and j, I want to choose a representative denoted by Tij, such that this is the terminal vertex which will be separated from the other terminals. And if you think about it, then you get like a bunch of different versions. So the first one is just the one that I mentioned, that from each terminal set you want to choose one, and you want to separate those terminal sets, or you want to choose one and separate it from everyone else in the other terminal set. You have these pairwise dependent representatives and so on. So you can come up with different versions, and we try to analyze this. These are all generalizations of the multi-way cut problem, and we try to analyze the approximability and inapproximability of these problems. And it turns out that in many cases, not surprisingly, we get the same approximation factor as multi-way cut, because it's you can somehow you can somehow apply similar techniques, although in some cases it's not straightforward. It's not like just reducing the problem to multi-way cut, but you, for example, in this setting, what you can do is that you can push through the proof of the best approximation algorithm for multi-way cut. You can push it through for this version as well. So it's does not follow from the results for multi-way cut, but you have to somehow be careful and verifying the results to get the same approximation factor. Here the interesting part is that we have hardness proofs for the case when we have unbounded number of terminal sets. It's still a question that what's the approximability of these problems. So we don't have any better bound than the inapproximability bound for multi-way cut. Okay, that's all. Thank you.